We will have Professor Palanker from Stanford University. So Professor Palanker is a physicist by training, and he has developed many lasers for daily care of patients, and he has now developed a new type of subretinal implant, and it's really a great pleasure for us to have Professor Palanker here in Paris.
Thank you, Serge, for the introduction, and I want to thank José-Alain Sahel for organizing the meeting, for the opportunity to speak here. So I'll present our development of photovoltaic arrays for restoration of sight. I want to start with the acknowledgement that I am a consultant to Pixium Vision. This is a French company here in Paris that commercializes this technology. So there was a very nice introduction and broad review, so I will not dwell on the introductory part. All I want to say is to bring your attention to the fact that we start with non-spiking neurons in retina, photoreceptors that respond to light by hyperpolarization, and then the signal is transmitted as a rate of neurotransmitter release to bipolar cells, either preserving the sign or reversing the sign to on and off pathways, and adjusting continuously again non-spiking neurons, potential of bipolar cells, and then it is converted into spiking in ganglion cells, and this digital code or binary code is basically what is transmitted to the brain through optic nerve. Therefore, the approaches to restoration of sight, which are based on encoding of stimulation of ganglion cells, are very different from the ones that are based on stimulation of bipolar cells, because these cells are non-spiking, and so we can adjust their response by controlling amplitude or duration of the pulse. While the stimulation of ganglion cells, the amplitude doesn't really matter. You have to be above the threshold of spike, elicitation of spike, and then all you need is to deliver appropriate frequency and with appropriate delays to basically transmit the code, and ideally to each type of 30 types of ganglion cells deliver its own code, which is very challenging. So these are very different approaches, and therefore the strategies are very different. So in our case, we are working also in subretinal space. Now the other important question is how much information we actually need to deliver, or how many pixels are required for different levels of vision. In normal vision, which is 20/20 visual acuity in American units, 6/6 in European, the frequencies on retina are 10 micrometer per cycle. So to sample it, we need to have pixels of at least 5 micrometer in size. And legal blindness in US is defined as 10 times worse acuity, and it requires pixels of at least 50 microns to just sample this information. I'm not talking about even encoding, just to deliver enough information for perception at that level. It was a very elegant, simple study by Pelli recently published, how many pixels we actually need to recognize simple objects in a familiar environment, assuming that vision is working perfectly, which is not the case with prosthetic vision, but let's assume that it is working, and we just deliver information, and this is binary black and white, and so the question is how many pixels actually it takes to recognize simple object in a familiar environment. And you probably will start recognizing now that this is stapler, and as you can see, it takes several thousands of pixels. So they did this with different objects, and the objects were half of the visual field of 25 degrees. And so it takes about 3,500 pixels to recognize simple object with no background. So background is actually removed by image processing, and with clutter background, it takes about twice number of pixels. So we need thousands of pixels to make this vision useful. Otherwise, it will be not even recognizing the objects. So how we deliver so many pixels and power them and so on in retina? It's one question. The second is very important fact that vision is actually based on eye scanning. If you would, first of all, we scan intentionally to recognize the most important features of the object. And we also scan continuously non-intentionally. This is a person that is fixating on a spot, and this is a mosaic of photoreceptors, and you can see that the eye is constantly moving. If I would attach a suction ring and immobilize the eye, the image would fade in about 10-15 seconds. So the eye movements is actually what enables vision of static objects. And therefore, it's very important to retain this feature. Otherwise, you will have to scan with your head, and even that is not complete compensation. So this feature is enabled if the image is, if the implant is light sensitive. So in our case, it is light sensitive, and the system is composed of video goggles with a camera that captures an image. Image is processed and presented in video goggles like Google Glass or night vision devices or gaming glasses. There are many on the market. Basically, it's a small display that is magnified through eyepiece, and you see an object which is presented on the display, projected on the retina, and a part of it which is projected on the implant is converted into current photovoltaically. So when light is on, current flows one way, light is off, it discharges back. We stimulate bipolar cells, they talk to ganglion cells through synapses, and then signal goes to the brain. And because this system is wireless, we can put these pixels together in small modules and load several modules in an implantation tool and deliver them in subretinal space by injection. So the surgery begins by injection, subretinal injection of fluid, which is a standard step in subretinal surgery. So we inject fluid and lift the retina and thereby provide access to subretinal space. We then make retinotomy of 1 millimeter in width, so it's a 20 gauge instrument. And then we deploy these modules in subretinal space and tile them to cover larger visual field. So even though we operate through small retinotomy, we can cover large visual field. Then retina is retouched and surgery is over. And everything else is optical. The image is captured by the camera, delivered via these goggles using pulse near-infrared light. We use near-infrared light because it's bright light, and we don't want to overwhelm the patient with bright light because they still have photoreceptors preserved outside this area. And image is projected with pulse light and converted into current in each pixel. Current flows from one electrode to another in the pixel, stimulate bipolar cells. They talk to ganglion cells, and this goes to the brain. So here are these arrays. I will be mostly focusing on the 70 micron pixels. They have 2 or 3 diodes in series to provide sufficient voltage. And current flows from one electrode called active to another, which is return. So each pixel has local return electrode to confine electric field. And we also have little gaps in this version of the device, 5 micron wide, to provide perfusion, which is very important for ex vivo measurements, but not as important for in vivo because retina has its own vasculature. What is important is that with this density of pixels, the limiting factor for grading visual acuity is the distance between adjacent rows. In our case, it's 65 microns, so keep this number in mind because I will be showing acuity we measure in animals, acuity we measure ex vivo, and this is the limiting factor. You cannot deliver more dense arrays than the sampling density, which is 65 microns. Now, in terms of number of pixels, if we fill the same area as Argus 2, which is 5 by 5 millimeters, we'll have about 5,000 pixels for, in an area where Argus 2 has 60 electrodes. And so it is a much larger number of pixels, and we hope it will be sufficient for recognition of objects. Another very important fact in vision is that contrast and acuity are related. And you can only see high resolution if you retain high contrast. And so to retain high contrast, we have local return electrodes. So when you activate many pixels together and you turn one off, for example, you will see it because local return electrodes localize the field. But if you don't have local return electrode and your return electrode is remote, for example, in a power supply somewhere, the electric field adds up, and when you turn one off, there is very little reduction in the potential, so you want to resolve it. Even though you have a lot of pixels, you basically will not see highly resolved image because the electrodes are not, return electrodes are not local. So in our case, we took care of that by having return electrode in every pixel. The price you pay for that is that the electric field confined not only laterally, but also axially. So when you make the electrodes smaller, your penetration depth becomes a limiting factor. So you have to be very close to electrodes, to cells to actually stimulate, and therefore the distance becomes a critical factor when you have local returns. Okay, and we will talk about it a little further, but let me first switch gears to what actually retina does in response to electrical stimulation. What we see is there are three types of responses. There is a pretty much immediate response, what we call short latency, coming from ganglion cells, if you stimulate them sufficiently strong pulse. There is a response coming from bipolar cells, we call it medium latency, it's tens of milliseconds. And then if there are photoreceptors, it comes several tens of milliseconds later, and this response is pretty much irrelevant for degenerate retina, but in healthy retina you do see response mediated by photoreceptors. And these are latencies of each of three responses, so ganglion cell response is within milliseconds, and it's decreasing with stimulus strength. This is our target, the inner retinal cells, bipolar cells. The response is in tens of milliseconds of latency, and then if there are photoreceptors, it's above 100 milliseconds or so. Now, since we are interested in stimulating selectively the inner retina, so we will benefit from retinal signal processing, we actually utilize the fact that bipolar cells are slower than ganglion cells, and the stimulation threshold of bipolar cells, shown in blue, continues to decrease as you increase pulse duration. And while the ganglion cells already at the real base, they saturate, this gap of stimulation threshold difference between two types of cells is increasing as you increase pulse duration. And so if you take a ratio of this, the ratio of this is increasing, and selectivity of stimulating inner retina is improving as you go to longer and longer pulses. And we actually utilize this effect and work with durations of 5 to 10 milliseconds to actually enable selective stimulation of bipolar cells. Okay, now how do we study retinal response? We do it two ways. Ex vivo, we place retina on a multi-electrode array and record from ganglion cells, and we can project these in normal light patterns and study response of normal retina. Or we can place photovoltaic array and stimulate with infrared light, so retina doesn't see it, but the electric current will stimulate the retina. And we can compare patterns elicited by both systems, compare apples to apples, so to say, prosthetic vision and normal vision. So what we see with prosthetic vision, there is a pulse of light, generate pulse of current, and then retina responds with a number of spikes, and we can relate them to different cells and count number of spikes per cell. And we see that it's increasing with brightness, like with normal retinal stimulation. It is increasing with pulse duration, like with normal retinal stimulation. And this basically is the foundation of restoration of sight. We can modulate perceptual brightness two ways, by amplitude and by duration, exactly like with normal vision. How much light we need? We need much more light than ambient. Ambient light on retina is no more than microwatt per square millimeter. We need several hundred times, almost 1,000 times more, and therefore, by the way, it's a similar number with optogenetics, but unlike optogenetics, we actually can use near-infrared light in order to avoid blinding the retina with this very bright light. So we use about 880 to 915 nanometers. And photoreceptors don't respond, but silicon responds very well, and so we can use this near-infrared light for this reason. Then the limit becomes only thermal, and the thermal limit is about 2 orders of magnitude below of what we actually need. Above. So our stimulation thresholds are 2 orders of magnitude below the ocular safety limit. So we have sufficient room for encoding many levels of gray below the ocular safety limit for near-infrared light. Okay, now very important theme obviously is resolution, and retina is arranged in converging circuits from photoreceptors to fewer number of bipolar cells and fewer number of ganglion cells, and the area that contributes to each ganglion cell is called receptive field. So we study it by playing spatiotemporal noise and recording response to spatial-temporal noise and identifying which cell responds to increase in light and which to decrease in light, and thereby we can map receptive fields. We can do the same with our photovoltaic array and measure response of this neuron to, say, this pixel. It's very strongly responding, and it's not responding to this one, so it basically can be mapped also as a receptive field. And if you compare the sizes of receptive field of normal and prosthetic vision, they are the same. And that means that the dominant factor now is the spread in the retinal network. The pixels, electrical pixels that we use in light stimulation pixels are smaller than the spread of the signal in red retina, which is on average about 240 micrometer receptive field, and our pixels are only 70. So it means that the dominant factor here is actually retinal spreading, therefore they are the same. But the vision is defined not by the average size of receptive field, but sub-units of receptive field, which go through different ganglion bipolar cells. And to measure it, we use one of the standard tests is a moving grating, alternating grating. With normal lighting, you would use just continuous illumination, but since we have to use pulsed light, we operate with pulse light, and if you would operate at low frequency, it would be very difficult to tell if it's actually moving or it is just flashing. Retina responds to both flash and motion, and so it's basically impossible to tell the difference. Therefore, we actually operate at a high frequency where flickering fuses. Flicker fusion occurs at approximately 20 Hertz for normal vision, and similar for prosthetic vision. And when you do it, I show a little slower so you can see that flickering light, but we operate actually faster and you basically don't see the flicker. And so now we can pay attention to motion, and what we see that retina now ignores the flicker and only responds to the change in the position of the image. You see it in the blue for normal vision, and you see it in red for prosthetic vision. So here what we see is that like in normal vision, there is flicker fusion with prosthetic vision, so it doesn't respond to every pulse if it's a high frequency. And there is adaptation to static image, so if the image doesn't change, retina doesn't respond. It responds only when the image is changing. And the same with prosthetic vision. So this is a benefit of going through the retinal network. We preserve these two very important features of vision: adaptation of flicker fusion, adaptation to static images. And if we plot now response, a number of spikes as a function of frequency or grating width, it drops to the noise level for normal vision at 29 microns. This is how well retina in reds responds. And with prosthetic vision, it drops to noise level at 67 microns, exactly matching the spacing between adjacent rows in our array. So basically, retina responds to as much information as we can deliver with this array. What is also interesting that we see two types of responses. One, we call it linear response. It basically occurs once in a cycle. So every second image is causing a response. Same prosthetic and for normal vision. And this is corresponds, for example, for on cells to increase in light. So when you increase in light, it goes through one bipolar cell to ganglion cell. It will respond. If you decrease it, it will not respond. And that's a linear response. We see the same with prosthetic vision. There is more interesting response when you see twice a cycle. We call it second harmonic. So every flip of an image, you see a response. So it's a second harmonic. You see here 2 cycles per, 2 responses per cycle of a movie. And we see the same with prosthetic vision. And the second harmonic responds to convergence of a nonlinear summation of 2 different subunits going through bipolar cells. So this one now received more light, it will be responding, and the response goes through ganglion cell. And if you flip the grating, this now will not respond because it's less light, but the right side will respond, and this response goes to ganglion cell. And we see exactly the same with prosthetic vision. So this process of response, if it would be linear summation, it would have no response, because all you will see is basically average brightness on this array. But with nonlinear summation, you see a response. And so this nonlinear summation enables a vision with much smaller feature size, a size of subunit, which is approximately 10 times better than average receptive field size in reds. And so we see that this high resolution with normal vision, all the cells are actually generating second harmonic. They are utilizing this subunit nonlinear summation, and we see the same with prosthetic vision. So it's another benefit of utilizing retinal network, that we actually have 10 times better resolution, because subunits, at least in reds, are about 10 times smaller than the average receptive fields, about 30 microns versus 240 of the average receptive field. So this is a big benefit if you utilize retinal network. If you would just stimulate ganglion cells, that would not be possible, because then the cell will respond to stimulus of a cell itself. Okay, so now contrast is another very important measure, and we see with normal, if you just make a step of lighting, we see response in normal retina to on, off, and on-off. And we see with prosthetic vision also modulating the contrast, response on, a little bit of on-off, and very little off. The off responses are primarily for remaining few photoreceptors in degenerate retina. We see they disappear actually with age. And, but the difference is that normal retina responds to small steps, a few percent of contrast very robustly, while prosthetic vision does not. It responds only to strong changes in contrast, but not to weak. And so if you plot it as in units of contrast, you see a very robust response of normal retina for both off and on, but no off responses for prosthetic vision and much worse contrast. So this is actually very significant. It means that we have to pre-process the image between the camera and the goggles to compensate for loss of contrast and prosthetic response of the retina. That's one of the benefits of having goggles actually outside the body, where you can do all the pre-processing before you project onto the chip. Okay, so now switching to in vivo, as I mentioned, we can implant multiple modules. This is a rabbit in subretinal space. These pixels actually look twice thicker than they are in reality because of the refractive index of silicon is 2.4 times higher than that of tissue. So they actually are resting on RP. They're 30 microns only thick. In rats, we actually go through the sclera implant, and this is the chip in subretinal space. Here is a retinal vasculature. This is a 70 micron chip again, and this is in the nuclear layers, the layers that we are actually targeting. You can see it here with subretinal chip actually. This is normal retina, so after subretinal implantation, photoreceptors disappear over a few weeks because they're separated from the RPE. And we create this local retinal degeneration, which allows us to study interaction between normal and prosthetic vision. That's a very important feature that in the same animal we can actually study response to normal vision, stimulation and prosthetic and compare them. And this local degeneration shown here is very similar to degeneration in RCS rats. You see preservation of in retina on RPE, and photoreceptors are practically gone. This degeneration of photoreceptors occurs in a matter of about 3 months, while the inner retina is preserved. Here is a retina after 1 year after implantation. You can see preservation of inner retina. The chip was removed, so it's now a little bent. In reality, it's actually very flat. And you can see that it's very close. The cells are very close to the chip. Okay, so now in animals, we can, as I said, compare response to visible light and prosthetic stimulation. In animals, we actually measure visual evoked potential, and we can study response to different patterns. So response to prosthetic stimulation shown in red and visible in green. You can see they're very similar. The only difference is that a prosthetic stimulation arrives earlier by about 20 or 30 milliseconds because we skip phototransduction. So we see that response is increasing along the sigmoidal curve with brightness, like with normal vision, but dynamic range is much smaller, only 1 order of magnitude. And it increases with duration, again over 1 order of magnitude. And then we check vision. So in our patients, we do double-blind experiment. So we ask patient to read in English, translate to Chinese and back. And the patients who fail, we let them resolve the gratings. So the gratings are decreasing in size again, and we basically monitor a response synchronized to motion. With normal vision, the response drops to noise level at 27 micron on retina, again, exactly like with multi-electrode ray ex vivo. And with prosthetic stimulation, it drops to noise level of 64 microns, again matching sampling in our array. This corresponds to 1 cycle per degree in rats. It will correspond normal vision and prosthetic to half a cycle. In human eye, it corresponds to 2.3 cycle per degree, this 64 micron spacing, which corresponds to acuity of about 20 over 256. And this is an anesthetized animal, so no eye motion. With eye movements, we oversample, and therefore we might actually see acuity, if everything goes well, even on a level of 20/200. We'll see what clinical trials will show. Another very interesting feature that we see is that with normal vision, background affects the stimulation, response to stimulation. So in a dim background, it takes less intensity of a flash to elicit response than with a bright background. We see very similar effect with prosthetic vision, and this is interaction of prosthetic and normal. So now this is animal with a chip in the middle and peripheral retina perfectly normal. We turn on light in a room, and we see that the threshold of prosthetic stimulation is shifting, which means that the retinal background light, which doesn't elicit any response by itself, no VP, it affects the response to prosthetic stimulation. It means that in patients with AMD that have normal peripheral vision and loss of central vision, the lighting in a room will affect actually response to prosthetic stimulation. So we have to take into account, like with normal vision, that what retina is responding to is basically contrast. And so you can correct this and relate flash brightness to background, and you will see that this collapses to one single curve, which basically is a contrast of the stimulus, and exactly the same with prosthetic stimulation, but now the contrast is related to background and visible light. So the normal vision and prosthetic vision interact. Okay, so going forward, we are decreasing now pixel size from 75 pitch to 40. And with this density, we'll have more than 10,000 pixels and 20 degrees of visual field. We're also integrating three-dimensional electrodes to provide better proximity to target layer, in the nuclear layer. And in summary, with this optical delivery of information, we can scale the number of pixels to thousands. The surgery is greatly simplified because there are no wires, and we inject this arrays in subretinal space. We retain normal relationship between the visual input and direction of gaze because the implant is optically active, so it's light sensitive. This is very important. We see that the stimulation thresholds are stable over 1 year of follow-up in animals. Modular design allows styling this many implants in subretinal space and increasing visual field. We retain high contrast because we have local returns. And we utilize network-mediated stimulation, which brings the benefits of flicker fusion at high frequencies, adaptation to static images, and linear nonlinear summation, which allows high resolution that we would achieve by stimulating just ganglion cells. With this 70 micron pixels, we achieved visual acuity on a level of half of normal in rats. In humans, as I mentioned, corresponds to 20/256. With eye scanning, we may see maybe 20/200, we'll see. And with the pixel size decreased by half, if everything goes well again, it would correspond to grating acuity to the level of 20/120. And if this indeed happens, this chip will become relevant for patients with AMD. So there was this question about AMD patients. So indeed, AMD patients are much more demanding because they preserve their vision on the level of at least 20/400 due to peripheral vision. And only if you get much better performance, it makes sense to implant in AMD patients. And we hope that we will be able to do it with this type of implant. Proximity to cells is sufficient with implants with pixels of 70 microns in size. And this array is now being commercialized by the Pixium Vision here in Paris, actually, and the clinical trials of the system, it's called Prima photovoltaic retinal implant, is scheduled for 2016. And the next generation, we hope to integrate pillar arrays to provide better proximity and decrease pixel size to 40 microns. So with that, I want to thank our team. Henri Lorac is performed most of the in vivo results that I presented. He actually is local from Serge's group, and I'm very grateful for excellent training he received here in Paris, and he is one of the very important members of our team. George Goetz worked on ex vivo results that I was showing is primarily his, also trained in Paris, and he is my graduate student, actually postdoc now. fabrication team from Department of Electrical Engineering, and we collaborate with UC Santa Cruz and Strathclyde in UK. And our former members of the team, and very important funding from NIH, DoD, Pixium Vision, and thank you for your attention.